The purpose of this project is to design a small-scale, high-efficiency turbine capable of converting fluid or wind energy into mechanical or electrical power, addressing the need for the sustainable, accessible energy solutions. The main objective is to create a turbine that is compact, efficient, and optimized for low-cost manufacturing while maintaining the reliable performance across various operating conditions. Background research shows that turbines used in hydroelectric dams, wind farms, microturbine systems have proven efficiency in renewable energy generation and applications in remote areas, small communities, portable power systems, and the industries seeking to reduce dependence on non-renewable resources.
So I took the video of the device in action in my dad's workshop and I utilized the high-powered fan that was in the shop because the motor I got off of Amazon, it needed the blades to spin very fast in order to actually turn on the red LED. And due to the blades being quite heavy in comparison to something you would find in comparison to something smaller and thinner, I needed that high wind speed in order to light the LED. So as you can see in the video, as I lower the vertical wind turbine towards the fan at an angle, as the blades speed up, the LED eventually turns on. And again, as I lift it off and I lower it again, just to show that while the blades are spinning fast enough, the LED turns on consistently.
The design process began with me and Russell researching different vertical axis wind turbines and evaluating blade geometries for low-speed environments and small-scale applications. We drew initial concepts and ended up going with Russell's to define the overall blade shape and the turbine layout while meeting our size constraints and keeping it portable. Then me, Russell, and Alp took the concepts and made them into 3D models using SolidWorks, where each individual component and assemblies were designed and accounted for tolerances for 3D printing and alignment for everything to fit properly. Then me and Russell refined the models and improved the integrity, the balance, and the airflow before starting to print and manufacturing the turbine.
So while undergoing the manufacturing process, the actual 3D printed parts were very simple and intuitive. The shaft went on top of the base and the blade slid into the slots on the shaft. But I'd like to note that my favorite part of the manufacturing process was the actual blade and shaft design and implementation. So here's our final version. And as you can see, each blade is slotted into these holes I cut out into the shaft, and they simply slide in and out. And that's because when designing the blades, I don't know if it shows up well, but I designed like this triangular like male extrusion, which then simply just slides in to this slot right here. I can show you that again. And that goes for all 3 of them. So throughout the designing and manufacturing process, that was just essentially the funnest and most creatively intuitive part, or at least I believe so. And again, through this design, we have no such need for nails or screws or any other such hardware in order to secure the blades. Instead, we just have this extrusion and slot system. So once all the 3D printed components were set, I glued the free turning motor to the base, which already had a hole cut out under for the wiring. So the only extra thing I had to do in regards to like the manufacturing setup was drill a small hole in the side, which I led the LED through. And then all that was left for me was just to connect the generator to the LED using two pieces of wire found in my dad's shop. So as you can see here, this is the hole that we left out originally for the geared motor, but we had issues with that, so we used this. But it still fit relatively well. I had to file out a little area though. But as you can see, the wires simply go through this hole and then out here through another hole that I drilled and then filed out so it can be smooth, which leads to the LED. So a design flaw we encountered was not having the hole for the LED already made, which led me to have to manually drill out and then file a small hole into the side of the base and then file it down in an attempt to make it more smooth and not stick out so much. Additionally, with the new generator, the actual shaft of the generator was much smaller than that of the geared motor. And I addressed this problem through packing the original hole that we extruded in the shaft. I packed that with epoxy. And then I found a plastic bit, which I then inserted into that epoxy-filled hole. Once that all hardened and it wasn't going anywhere, I then used like a tiny drill bit to drill a space for the generator shaft to connect to. Then I packed that with glue, and then I connected the 3D printed shaft with the motor. And if I hold it at an angle, I believe you can see the yellow plastic bit. So a design failure we encountered was with the tapers in the shaft columns. So originally we had these small little extrusions in each shaft column, about half an inch to the bottom of the shaft. This was in order to stop the blades from sliding down the entire way and keep them in a nice position. However, during the 3D printing process, we don't know exactly what happened, but essentially the 3D printer messed up that feature, and those stoppers just came out too small to have any use, and the blades just kept sliding all the way down. So what I did to fix this was, again, with just some epoxy. With some epoxy, I did this all around at an even height, about, again, half an inch from the base. I just packed in some epoxy, waited for it to harden, and then when I slid the blades down, it gets stopped at this epoxy structure I made, which ended up working perfectly once it hardened, and the blades don't go anywhere and they're all level.
In the future, the wind turbine can be optimized by improving the aerodynamics of the blade in the curvature and adding more blades to increase the efficiency of the turbine. Improving the alignment of the shaft can help stabilize it better and give a better rotational performance. And choosing a more efficient low-speed generator could increase the electrical output that the turbine can generate. Also, reducing the weight could improve the stability and the portability of it, making the design more practical for real-world and educational applications.